The Solid Edge portfolio offers industry-leading design capabilities, simulation, manufacturing, data management, and a vast offering of additional capabilities to create a fully customised solution set for your digital models. Our tour today will be looking at some of the next generation design tools, which include generative design, convergent modelling techniques, and additive manufacturing. Generative design is a process whereby the computer will create an optimised design for us based on the use criteria of the part. This allows us to ensure our components are as lightweight as possible while minimising material usage and saving costs, all whilst maintaining the structural integrity required. The output from generative design is a mesh model. In the past, it's been difficult to work with these types of models. However, Siemens' convergent modelling technology now makes this possible, and edits can easily be made to any mesh model. Let's take a look at the core area of generative design. As a quick example, we'll first take a look at this Bernina sewing machine and focus on its internal mechanical components. These components are positioned by a framework which will typically be modelled with several features which define the required geometry, all in order to make sure it's strong enough to support all the components connected to it. Now consider a process where you only design the basic shape, as you can see here, and let generative design figure out the rest. Generative design never adds material, it only removes material, so it's important to define the areas of the model that need to be preserved. Not only can you apply loads and constraints, as we're doing here, to ensure the model can withstand its standard operating conditions, but also you have the capability to select areas on the model that need to be preserved, such as mounting and locating features. Once the model's design requirements and constraints have been defined, generative design uses this important input to generate a very smooth organic shape model that fits the design needs you're looking for. Not only does generative design save design time, but also helps to reduce material costs by reducing weight. The result provides an organic, smooth mesh body ready for additive manufacturing. Generative design is useful in many different industries, including aerospace, automotive, and more. As an example, consider this simple bearing block. Using an iterative process, multiple revisions of the design can quickly be generated, helping you achieve the best possible lightweight solution for your needs, and yet still ensure it's strong enough to withstand the workloads it will face during operation. As another example, let's consider this mechanical pedal assembly. Currently, the pedal itself is an assembly made up of about 6 separate fabricated parts. This can be expensive to produce. Our interest is to reduce material, weight, manufacturing and assembly costs, but at the same time ensure structural integrity. This is a perfect application for generative design. To start with, we'll replace the pedal assembly with a basic shaped model. By moving the pedal in its range of motion, it becomes apparent how this design is supposed to work. It helps us to better understand what aspects of the part's geometry are important for the pedal to work correctly. Now we have a better understanding of how it works, we can begin to set up the generative design process for this part. We'll edit the part and turn off any background components. This lets us focus more on the design of the part itself. Generative design is fully integrated into Solid Edge, and all the commands are right at your fingertips. The ribbon presents the 10 key commands for generative design in a logical sequence, guiding the user through the steps they need to complete in order to set up and run a generative design study. First, we just need to ensure a material is defined. Once a study is created, we can then go through the process of selecting preserved regions or areas of the model we want to keep. Here we can define an offset value which will preserve the hull and the boss geometry. It's obvious where the force is to be applied on the pedal. The direction of the force can easily be set by using the Solid Edge steering wheel. The value of the force can be defined along with an offset. The final thing to do is to set the constraints on the model. For this study, we'll set a fixed constraint on both holes on each side of the bottom pocket. Again, we'll define an offset. We'll also fix the rear pivoting boss. Remember, the option to define an offset helps preserve the geometry in the part needed for it to function properly when finished. After defining all the study options, we're ready to generate the new design. The Generate dialog provides slider bars so that you can make a quick adjustment for study quality and a target mass. For this first example, we'll reduce the mass by only 20% to give us a baseline. Allowable stress values are shown as well as a factor of safety. Let's generate the model. Once generated, we can take a look at the results. Here we can see the areas of the model where the stress is most concentrated, just below the pedal. Remember though, we're still within the allowable stress for this part given our factor of safety. We can run the study again and make some adjustments. Here we'll reduce the mass a little more by changing it to 40% to see what the results look like. Immediately we can see most of the material removal occurs under the pedal. Depending on the user's preference, multiple studies can be created and each study's settings are easily accessible through the edge bar for quick changes. This iterative process to generative design makes it easy to adjust any parameters in order to get the best possible design as fast as possible. Before generating the last study, let's make a quick change by preserving the sides of the pedal in order to give it more strength and stability. Once again, this is just a case of picking the required geometry and entering an appropriate offset value. This time we'll also reduce the mass of the part by 60%. Notice the result shows a huge reduction in material, and yet the super smooth mesh model has enough strength to withstand the forces it will be put under during everyday use. Displaying the background parts in the assembly gives us a clear idea how the new pedal fits within the design and interacts with the other components. The huge advantages in using Solid Edge to create and work with these generative designs, which are essentially mesh models, is when it comes to the creation of additional features that the design may need. With Solid Edge, adding and removing material is simple and fast. For example, a cutout can be added to the lower boss for the purpose of placing a bushing. The use of standard modelling tools make this process quick and easy by picking up on background parts in the assembly. We'll also add some geometry too. In this case, we'll add the part number to our part by first placing text, then extruding that text into the design. The power of Siemens convergent modelling techniques available in Solid Edge provide an engineer with the ability to further the design of mesh models fast and easy. Returning to the top level assembly, we can see the finished design of the pedal in motion with the rest of the assembly. So generative design gives us the capability to generate low-cost, lightweight mesh models that can then be modified through convergent modelling techniques. The only question that remains is how can we manufacture these models? Let's go back into the new pedal design and answer that question. Solid Edge provides the capabilities for you to take your designs directly to the additive manufacturing process. The 3D Print tab provides several options to get your designs manufactured. We'll start by previewing this model. This allows us to check on its quality and then adjust the tolerance of the facets if required. If you have access to a local 3D printer within your company, then your part can be printed right from your desktop. Here's an example of reading our design into the Fabricam 3D printer. The step-by-step approach first allows us to change the layout of the part so it's in a better orientation for printing. The Settle option uses kinematics to drop the model onto the printer bed in the best orientation. We can define the quality of the print, review any overhangs where support material may be needed, select a material, and finally make changes to advanced layout and settings. Now your in-house printer might be ideal for creating one-off prototype parts in plastic materials, but what if you don't have such a printer available or you want to choose the best material for the final part, including for example steel, aluminium, tungsten, ceramics or wax? Solid Edge offers the capability to order the 3D print through an online service called Through Your Mind. Through this interface you can check the printability and scale of your model, then browse through the different material options, using filters if necessary. These all include the price, print method and lead times. Once we select a desired material, we can then choose which preferred company we want to use for the actual 3D printing. The idea here is to give you all of the options needed so that you can get your parts printed as quickly and as cost effectively as possible. When you think about next generation design, Think about Solid Edge and the state-of-the-art next-generation tools it offers to get your job done right first time. From generative design for creating a lightweight, very smooth mesh model, to convergent modelling, which gives you the capability to further the design and easily edit the mesh model, to state-of-the-art 3D printing capabilities. Solid Edge, design better.